Okay, in this tutorial we're going to discuss the basics of doing Monte Carlo simulations in R. And this is really a very basic demonstration. I'm not going to discuss the theory at all of Monte Carlo simulations or anything like that. Some of you coming from a computer science background probably have some background in it. Those of you from more biological backgrounds probably don't. That's fine. As long as we understand from your readings and from this tutorial what the goal is, that's really all I care about for this. And again, I'll write down Monte Carlo in case you want to look it up, and I'm sure that Gotelli and Ellison has a little bit of discussion of it. So the first question you need to ask yourself is, well, what do I mean by simulate? And here we're really thinking about simulating data. We're going to be generating fake data, simulated data, from some underlying process. And we get to play it as a minor deity and actually generate that data or generate that actual process. We know what it is. We know the deterministic and stochastic components that we're going to do. Here we're going to use a very, very simple one. So why would something like that, generating this fake data, this simulated data, why might that be useful? Or be useful tool in statistics? Well, it turns out there's multiple reasons. For our class, we're mostly interested in it as a tool to teach us the ideas of sampling and sort of the basic ideas of one concept of probability about repeated sampling and what we expect to observe based on this repeated sampling, as we discussed in class. And of course, the other useful tool that we don't get to talk about in this class is that these approaches are very, very useful actually for making statistical inferences. And many of these Monte Carlo approaches actually fall under the rubric of what we might call parametric bootstrapping. And parametric bootstrapping is one particular example of a Monte Carlo simulation, which I do want to make the point that this parametric bootstrapping, we don't really need to know this for this class, but parametric bootstrapping is different than bootstrapping. You will often hear when people just say bootstrapping in statistics, they often mean non-parametric bootstrapping, which actually uses the observed data from your experiment. I also do want to make the point, and Charles will, I'm sure, be happy to discuss this in class as well, is when we talk about simulating data, this is a very different process than, say, what we do with Avita, with digital organisms. The goal here is, the simulated organisms are going through real processes. Here we're really doing simulations at a much more basic level. I'm also going to say we're not going to discuss at all in this tutorial any of the computational or mathematical details of either generating random numbers or how we know they're random or pseudo-random. We're just going to assume that they're close enough to random for our processes in the moment. And R has a lot of facilities for generating random numbers, and we're going to start with generating a simple random number from a uniform distribution on 0 and 1. So basically, we want to generate random numbers between 0 and 1, and we're going to start by generating just a single number, and we're going to use R unif, and that stands for random, because it's going to generate a random number from a uniform distribution. Unif is the short for uniform. We're going to generate one number, n equals 1, and we're setting the boundaries where the minimum is 0 and the maximum is 1. And this is the general format you're going to see for a lot of these. It's going to be R name of dist. So that's going to be R, you want to generate random numbers from some kind of distribution. So we do that, and voila, we get some number between 0 and 1. Well, by that self, not so useful. But of course, we can do this for, say, 1,000 numbers and generate 1,000 random numbers between 0 and 1. Continuous value, and we get a whole big list, and that's perhaps useful. And in fact, we can write a shorter version of it, because the default arguments for a uniform is assuming it's bounded between 0 and 1, min and max of 0 and 1 respectively, and so we can do that same thing, and we'll get 1,000 different numbers in this particular case. And we could ask, okay, well, let's draw a histogram of this data. What should it look like? And so I'd like you, before I run this, to think, and maybe even pause, what should a histogram of 1,000 random numbers look like? So first we'll just call those 1,000 random numbers. Pause it, think about it. Now we can look, and I'll bring the plot over to this window, and hopefully you can see that it's sort of more or less uniform across 0 to 1, which is what we expect. This is a uniform distribution. We shouldn't see a bell-shaped curve or anything, which would be a Gaussian or normal distribution. Okay, we can do this for all sorts of distributions. So for instance, what if we wanted to look at 100 draws from a normal distribution, sometimes called a Gaussian distribution, that has a mean of 5 and a standard deviation equal to 2? And a short form way of writing that is we can say the variable that we're drawing is normally distributed, so tilde means is distributed as, it's a short way of putting that, so it's distributed as a normal distribution with mean 5, standard deviation of 2. So we do that in this particular case by using the rnorm function, and again we're going to do n equals 100 for 100 random draws with a mean of 5, standard deviation of 2. We run this whole line, and now in random.normal.100 we've generated this. So we can ask, okay, let's take a look at some of the plots. And we'll just do some very basic plotting. We'll use just the basic plot, box plot, and hist. The par functions, I'm just setting some options for what the graphical device will look like. So I'm going to make the palette have 3 rows and 1 column so we can put all 3 plots on it. And we run that, and I bring this window over. And it might be a little bit smaller on your screen, but hopefully you're running this yourself. And the first one is just showing you the value for each of those random normal deviates from that distribution of mean 5 and standard deviation of 2. The first one is just indexed based on where it is in that vector of 100 random draws. The next one's a standard blocks plot with the black line being the median and the 25th and 75th% quartiles being the end of the box, and then I can't remember how R is specifying the bars, probably the 95th percent. And then a histogram of it, which is more or less showing a normal distribution, and that has a little bit to do with how histogram, the hist function, does things, and we can worry about that later. More importantly, we can also use this to, say, ask questions about, let me separate these into 2 different lines. That's a better, easier way of doing it. We don't need the semicolon. Let's say, well, what's the mean of these 100 random normal values? And so you should ask yourself, well, what distribution did we start with? A distribution of mean of 5 and standard deviation of 2. What does that suggest that this mean should be at least similar to, or perhaps exactly equal to? And you should ask yourself, which of those do you expect? Run that, and we have a mean of 4.8. So if you remember, it was sampled from a distribution with a mean of 5 and standard deviation of 2, but our mean was 4.8 and our standard deviation was 2.27. They're close, but neither is identical. Well, why not? Well, because we only generated 100 random draws from that distribution. And so we expect, based on sampling, like we discussed in lecture, that it's not going to be exactly equal to that. So our mean is not exactly equal to 5, our standard deviation is not exactly equal to 2. And so what would happen if we repeated that experiment 4 times? So let's just do that. We'll generate 100 draws from that normal distribution of mean of 5 and standard deviation of 2, and we'll just call these 4 variables random.normal.100.1 through .4. Run those, and let's plot those. So again, I'm going to change the parameters. So I'm going to have this now be set to have, we're going to make histograms with for each of these sets, so 2 by 2, so 2 columns by 2 rows. And we're going to run that. And one of the things you might notice here is that clearly it's different data. The distributions are a little bit off from one each other. We probably should have set some of the things so that we had equal numbers of breaks between the bars, but even so you can see that by and large they're showing somewhat different distributions, because they're each an independent draw of 100 observations. Even though they're from the same distribution, they're a little bit different than one another. And we could actually say, well, let's look at the means for all 4 of those and see what we get. And we get 4 different means, all reasonably close to 5, but none exactly equal to 5. One's 5.04, pretty close, but you also have one which is 5.268, so a little bit off. And that's, again, the point. They're all close to, but not exactly equal to 5. And even if we did 100,000 or a million, we can ask the question, would we still get it, will it be exactly equal to 5, or will it be just very close to 5? Will it be closer to 5 if we do more of them? And these are questions that we'll address in class and exercise. So of course there's more efficient ways of performing these simulations. Excuse me. And if you've done the previous tutorials, you've learned about the replicate function, and we're going to do exactly what we did there. We're going to store, we're going to do the 4 sets of 100 random draws each from that same distribution. And so we use the replicate function to say, okay, let's draw 100 random variables from that distribution, and let's repeat that n equals 4 times. And we'll store all of those. We can run it. And if we take a look at it, you'll actually see that we now have a data set where we have 4 columns by 100 rows, and each column represents one of those sets of 100 draws from that distribution. And we can use other apply-like functions, just like apply itself, to actually make some histograms. So this is just like we did before, but these are 4, they're going to look a little bit different because these are 4 new sets of random draws that we've done, but gives you the same basic idea here. And we can continue to use the apply function to do this for the means and standard deviation. So let's just run through both mean and standard deviation. Again, make sure that you have read the apply-like and gone through the apply-like function tutorial. It's worth noticing, you've probably already seen me start to do this, is that if you actually use the order of arguments correctly for particular functions, you don't actually have to specify the names of the functions. It's actually a bad habit to get into, and I'm trying to clean up my code, so try not to do that. But it is convenient. Okay, so let's run those apply-likes for the means and standard deviations. And so again, we get means all close to but not equal to 5, and standard deviations all close to but not exactly equal to 2 for the standard deviations. And we'll discuss in a later class when we start talking about the law of large numbers, about for expectations like means versus higher moments like the standard deviation, how quickly do they approach the theoretical value, which we will discuss later on in this class. But that's maybe something worth keeping in mind if you haven't already read it, is the law of large numbers. I should probably also put expectations, although hopefully you have read about both of those in your readings already. But please come ask me questions if you aren't sure what I'm talking about. So the advantage of this approach is you can actually even use, say, the summary function just to get all the information you might need. So we can actually get the means, medians, and whatever you want for each of those 4 random variables, or extracting in all sorts of other way. The other thing that we can use this for, which is quite helpful, is we can say, not only are we interested in computing, so we've computed those 4 sets of random variables, and each random variable represents 100 draws from that distribution of mean of 5 and standard deviation of 2 from a normal distribution. Let's compute those means, so we're using this apply-like function again to compute the means, just like we did above, exactly the same. So we can redo it. We'll get those 4 means, but we can actually ask an important question. How much spread is there between our experimental trials? So now here's a new thing, experimental trials. What are we talking about? Well, the basic idea is each of those 100 draws from that distribution represents a single trial. You can kind of think about it as if we had a big bag of beans, it was with a number written on each of them from this distribution, it would be the 100 beans we had pulled out with those numbers on them. And then we put them back in, shake it up, and do it again. And just repeat that over and over and over again. And each of those is an experimental trial. That 100 draws from the distribution represents our experimental trial. It's the size of our experiment. And we've repeated that experiment with 100 observations 4 times. So how much variation do we see between those 4? So we can take that output, and because R is vectorized, it's just a vector, and we just ask, well, what's the standard deviation? And the standard deviation between those 4 means is 0.09. So it tells us something about the spread of the experiments. Okay, well, why is that important? Well, we're going to learn, again, it's relating to the law of large numbers, and a couple of other things we'll learn in a few lectures exactly how this is useful. But let's sort of think about this. Again, what do we expect to see if we repeat this set of experiments, but instead of doing 100 random draws, we do, say, 25 draws? So what we do is the exact same sort of thing as before, but instead of having our norm, the n equals 100, we're going to have n equals 25. So the mean is still the same, 5. Standard deviation is still the same. So we're still drawing from the same distribution, just fewer samples. And now we do that. And I'm just going to jump to the looking at the standard deviations. They're actually a little bit further away from 2. And the means, let's look at the means. I apologize. Don't worry about that previous line. The means, well, they're all actually in this case below 5, but that's just stochastic. But you may notice that they're maybe a little bit further away from 5 than the samples when we did 100 draws. But we can also ask what that sampling, if we compare the means, the 4 means that we've computed from each of these experimental trials, is there more or less variation than we previously see. Well, we can't just do this once and make a statement about it, but in general, you should think about what might you expect, and we'll in class do exactly these activities. And how about if we have a much larger sample? We can do the same thing. Here, instead of having 100, we do 1,000. And we can ask the same thing and look at, excuse me, how much variation we see among those. Okay. And we can actually ask, do we see a pattern in the precisions for the means at these different levels? Oh, it looks like I didn't do one of them, but that's okay. And the same for the standard deviation. We can ask the same question. I'll not worry about going above and fixing that, because I'll let you sort of think about what patterns do we expect to see. And really, you should try doing this over and over again a little bit to actually play with it. So I definitely suggest pausing this, playing with this for a little bit, and see what's going on. Now, we want to do this often, and I'm just going to do a very quick example of this, well, this is just drawing from a very simple distribution. In our case, we just drew from a distribution with a mean of 5 and a standard deviation of 2 from a normal distribution. But we can use these for more complicated models. So we can think about a model like a simple regression model, where we can say the variables that we're drawing, which we'll just call y here, which we can think about as our observations, are going to be distributed or modeled as in normal distributions with this model, a plus b times x. So a line, we're making a line, with some kind of standard deviation. So our mean now is some deterministic component, some function of an intercept and a slope times our random variable, or another random variable, to generate a new random variable, which is going to be y. So again, these are our explanatory variable would be our x, y is our response variable, and we get to play the role of a minor deity and determine what that is beforehand. So here, what we'll do, I'm just going to set up an empty plot, and I'll show it to you in a second, but we're going to, again, say the intercept, a, is equal to 5, the slope, b, is equal to 0.7, and then x in this case is going to be a sequence from 2 to 20, so maybe it was some experiment we did where we could manipulate whatever the response variable is, say maybe how much nutrients we put in or resources we put into a particular environment. And then we're going to actually write out the deterministic part of the model. So we're going to write out essentially the equation for the line, and that we're going to call that y underscore fixed. That's the equation for the line. So let's just do that. And if we actually look at y underscore fixed, it's just going to be a set of numbers. And we do this over and over again, we get the same thing, because so far we haven't introduced any stochasticity. And we can plot that, and that's really just going to be the deterministic component of the model. So if we did this over and over and over again, we'd expect to get exactly that same line, the same relationship between y and x. And I'm just going to do the AB line to just draw the straight line through it. But of course, real data is generated by various stochastic processes or things we just don't know, even if they're deterministic, so we have to incorporate variation. So what we're going to do here is just do the same thing we did before, but we're just going to say, it's coming from a normal distribution with a mean of that deterministic part of the model, y underscore fixed, and with some amount of residual variation. We, again, are at the moment playing the role of we determine how much that is. In real data, we don't know that, but that's besides the point for this exercise. And then the length, we want to make sure we match how many random variables we're generating based on how many observations we started with. So it's going to be length of x, which was from 2 to 20 before. And so we do that, and now we can draw this, and what we'll see is that, and I'll put the line on it, and I'll bring this back over for everyone to see, is that the same underlying deterministic process is at hand, but there is now an additional stochastic component. And we could use this, and I don't think we really need to, is we can use this as a model of, well, how well does certain statistical methods, like fitting a regression using least squared estimation, do at estimating these parameters? Because we know beforehand, in this particular case, what those parameters are supposed to be, but the sampling, the sample size, and the amount of stochasticity introduced will influence that. And if we actually do that, we can actually take a look that don't worry about the confidence intervals, that our estimate for the intercept is 3.9, despite the fact that our original intercept was going to be I believe we had it as 4, is that right? Above 5 even. Of 5, and the slope, our estimate is 0.73, which is actually pretty close to what we had inputted, what we had actually done on purpose. More importantly, we can look back and say, well, we know that first black solid line we drew here is the true values, the true estimates. This dashed line is what we estimate with the simulated data. So we can ask how, the degree of uncertainty, what would happen, what would we expect to happen if we increased our sample size? Should it get closer to that black line? What should happen? Okay, the rest of it I don't think we need to point. It's just if you're doing sampling of specific numbers, how you might want to do it, and I'll just let you read ahead. But what we've talked about is really at the heart. Getting the basics of that method will allow you to now run simulations, especially if you can integrate this with for loops or some of the apply-like functions. So play around with it a little bit, and in class we'll do some exercises.